Hi, my name is Stefano Moia, and in the next minutes we're going to go through a tutorial on how to remove physiological fluctuation from MRI data. In this tutorial we will mainly focus on preprocessing the physiological data and then preparing the metrics to do physiological denoising, not the physiological denoising step per se. I have something to disclose, and that something is that I am a member of the PhysiOpi community. And I'm disclosing this because all of the software presented here is supported by the PhysiOpi community, which means that I might be biased to it, but it also means that there might be newer versions of this software that is supported by a full community available with more functionalities or some differences from what I'm presenting here. And this might be already happening by the time you are looking at this video. This means that this tutorial is obsolete, possibly. Hopefully. Sorry about that, but we're trying to do the best that we can, both with the latest software in these tutorials and with the PhysiOpi community itself, to maintain better software. And also that it means that you should check out the relevant software documentation for the latest version of the software and the latest functionalities, but also check out this repository on GitHub, github.com/smoia/OHBM 2023 notes tutorial, where you will be able to find more information and some test data if you don't have any. Alright, before we start with this tutorial, it would be good if you checked these other talks from this educational course. If you're here, it means that probably you know that there's this educational course and you probably watched these videos that are coming before me in time. But just in case, it's good to check out the talk from Molly Bright, that brain you are scanning is inside a living, breathing human, and it shows, because that's where there's an introduction to physiological signals. And for instance, if you're not acquainted with the topic of physiological data, that's the place to start. Okay, so the first thing that we're going to do is to create the virtual environment in which we're going to use big data and physical noise. So to start with, I'm going to create the virtual environment itself. I'm going to call this virtual environment OHBM 2023 noise. That's just the name. I am going to source activate this virtual environment. By the way, this step is not mandatory, it's optional. It's just because I prefer to have this tutorial running on something that you will be able to replicate if you want, with the list of toolboxes and versions that I'm installing this moment, that you will be able to get from the GitHub repository. We'll start the virtual environment itself. And I'm already going to move to the folder where I have my files, and I am going to start some installing now. So the first thing that we want to install is WXPython. WXPython is a library that deals with graphic user interfaces, and that's important for big data. Now, WXPython is a bit and I do not know by heart how to do these for every OS, and for my OS either. I found online that the best way to do it is using pip3 install no cache and then getting the link directly from the WXPython website. In my case, because I have GTK3 and I use Ubuntu 20.04, this is what I want to use. So it's pip3 install no cache, and then the -f is just to get the link to a direct website and not PyPy, and then my link is the one that you see here with the extras: WXPython, WXPython 4, extras, Linux, GTK3, Ubuntu 20.04. I do want the version 4.2.0, so I fixed it in Miedema, that is called Hands and Sensors On, a practical guide to acquiring your own physiological data. And that's where Mary's explains how to convert physiological data into bits or text format with phys2bits. That's where we're going to start with our data. And so it's good, if something seems odd, that you check out that tutorial to know what happened to this data before I start using them. I will try to make this talk as generic as possible, but if you see that there's something that is not given for granted, it's possibly in our tutorial. Finally, there's the talk from Jingyu and Chen, methods for mitigating physiological noise in fMRI time series, that contains the theory behind this tutorial. And so if you're not acquainted with that theory, it's good to go check it out before starting this practice. It's going to take some time to download it, so I'm going to do some editing here for you not to be able to wait for it. Hello. Okay, it's almost done, and with the power of editing, you luckily skipped the waiting. It's gonna finish installing a couple of other libraries, dependencies of WX and then we will be able to start installing the main libraries that we need for this tutorial. So while we wait, the reason for which we decided to use PhysioPy's libraries for these tutorials, all of the educational course, by the way, is based on PhysioPy or related software, is mainly because of the easiness to install this software, and as well as like the fact that they are in Python, the fact that they are supported by a community, and so all of these decisions made us choose these softwares. However, we asked other software developers to record a power pitch about their software, and we will show this pitch, these videos at the educational course itself, at the live version of the educational course, and we might upload them on the PhysioPy website, so you will be able to find alternatives if you prefer other alternatives in MATLAB or still in Python, or in C or in other ways, but so that you have a more general view of what is out there and what you can use. Alright, so we installed WX Python. That was the longest installation that we have to go through for this tutorial. I'm going to install now 3 things. The first one is pick that, as we discussed before. The second one is fist to denoise, and the third one is IPython. And finally, Matplotlib will be installed by PickThat itself, and it's gonna install a version before 3.7.0. We're working now on fixing a couple of things so that whatever Matplotlib is there is okay, but just in case, we want to be sure that it's working, and recently Matplotlib gave a deprecation, so we had to deal with that. So I already installed, like already downloaded all of these packages before, so now you see that it went very quickly through installation. It might not be the case for you, but it should be fine in any case. Alright, now we have installed everything, we are ready to start this tutorial per se. And we're back at the terminal, and we are already in the folder where we have the data. I'm going to now start IPython, which is where we're going to work with everything. You see on the left of my screen, you see the steps that I'm going to go through for this tutorial. I'm going to make them a bit larger just because maybe it's easier to see. On the right you have my terminal. I might just copy paste a bunch of stuff. Be patient with me, but you will find this step.py file in the GitHub repository I was talking to you about before. So we're gonna do some importing. That's NumPy, Matplotlib, PicDat. We're gonna install some functions from fDenoise. We're not gonna import everything. Just the heart rate variability, the variance of time, and then the export metrics from the utilities. We're going to start with reading the data itself. So to read the data, I'm just going to do a data equal to numpy jump from txt, and then my file is called subject 7 session 5 task run 1 physio.tsv.gz, and that's what I want to use. It's going to take a little bit of time because this is a very big data set. It was collected at 10,000 hertz of sampling rate. It is 10 minutes of data, a bit more actually, so it takes some time for NumPy to read it in for the first time. Okay, as I said before, there are different, like this is a file that comes from fizz2bits. We processed that, like it was acquired with a Biopack system, and it was processed into bits using fizz2bits. And so I know the structure that is represented here, and it's the structure that we expect this data to be in. And so there is a couple of things that I'm gonna give for granted, and again, otherwise just check out Mary's tutorial about how to use fizz2bits. The first one is that I know that there's channels in this data, and if I check the shape, you see that there's six columns in this data. The column number 0, the first column, is the time. So actually, if I do 0, you see that there it's basically an advancing array. If you plot it with Matplotlib, you will see a line. And the point in which this line crosses 0 is where the fMRI data started, as I said before. So we are going to find that point. It's fairly easy. It's just numpy argmax. We're going to get the index of that. If we check for the index, it's somewhere in the 373,000, which basically means something around second 37, around that, because of our sampling rate. We're going to then extract the respiratory belt. I already know that the respiratory belt is in channel 1, and so I can do that very easily. But again, Mary shows how to also get some picture of the content of the channels in her tutorial with fizz2bits, so that it's easier for you to find the data that you're looking for. And so for instance here, what I'm going to do is I'm going to initialize the object of PicDat. It's going to be here, so it's the object is called physio, and it's going to be data. I am going to take the index 0, and I'm going to start from there because I don't care about the data that comes before. You might for other reasons, and for instance, if you're going to watch Christina Zvolanek's tutorial later that comes after in the educational course, she will not do this step, but just in case, I want to start from my index 0. I know that this data is collected at 10,000 hertz, and that's the sampling frequency that I am going to declare during the object. It is necessary to declare both the data and the sampling frequency, because the steps that will come after will require this. Once I did that, I am going to plot it for the first time. And to plot it for the first time, I have picked that plot physio utility, with which I'm going to plot the object, and I'm going to use plt show, which is the matplotlib plot show command, because otherwise it will not open this window for me. Start, here's what we need to actually get started. You will need a computer with Python above 3.6 installed. 3.7 is great, 3.8 is great. Above versions should work as well. Optionally, you want to use IPython. I will be using IPython from my terminal. IPython is an enriched terminal for Python. You can install it with pip, with PyPy. So it's pip install IPython. You will have to install PicDat and fzdenoise. Optionally, you can add matplotlib, fzbits, and fzcvr. PicDat and fzdenoise will be the main software that we're going to use today. We're going to also use matplotlib for visualizations. fzbits and fzcvr are extras that you can install if here this is our data. And if you look into our data, it is a respiratory data. You can see that because of the time of between the different peaks. So for instance, here we go from second 200 to second 210, and you see more or less 3 respirations, which is more or less correct. It's more or less like 3 seconds per peak. It's maybe a bit fast as a respiration in this case, but it's not that weird. If you zoom in a bit more, you see that it's not super perfect, it's not super clean. There's a little bit of noise here and there, and so the first thing that we're going to do is remove part of this noise that is actually high frequencies. So I'm going to close this window, and the first thing that I want to do is downsample the signal. Why we are downsampling the signal? Because again, like we work with functional MRI data, our TRs are nowadays they can be very fast, but normally our TR is around 1 second or more, and so the 10,000 hertz that we collected this physiological data at is not so important for this application. That doesn't mean that it's not important in general, but for this application it's a bit too much. Because of that, then I'm gonna create a new object that is I'm gonna call ph, and that's I'm gonna then run the operation of interpolating the physiological data, which is interpolate physio. I'm going to declare my object from before. I'm going to declare the new frequency, sample frequency, and I want to do this interpolation in a linear fashion, in a linear way. So that's what I'm going to declare. Now this already automatically applied a sort of high pass filter. Sorry, a sort of low pass filter, because every frequency above 40 hertz is lost at this point. But we still want to apply another low pass filter to be a bit more conservative and have a bit more smooth data. And in this case, we're going to do it with the operation that is filter physio. And this filter physio we're going to run on our object. I want my filtering to remove everything above 2 hertz. That's quite a conservative amount for this type of data. It doesn't work with all data, but this type of data is for this type of data is fine. We are gonna run this filter low pass, which means that we're gonna keep everything every frequency below 2, and this is a Butterworth filter, which means that we can declare an order for the filter itself. In this case, I'm choosing order 7, so that the function to basically mute, let's say, to filter the frequencies above 2 is fairly steep. This done, we should see that our data changed a little bit, not too much, just a little bit. And now if we zoom in our data, we will see that it's still somewhat noisy, but not as noisy as before. It's a bit more smooth, and that's what we're looking for. and again, like if we go in, like we see this is typical response of a respiratory belt. Maybe not the best, but still a typical response. And just for you to know, this is fairly standard respiratory belt as it looks like. If you're interested in seeing data that are not standard, data that are corrupted, or data that shouldn't look like they should, there is material in previous years of OHBM. We ran the same educational course last year. There's a talk about basically artifacts in this data, and we will have some of these pictures of bad data on our website in PhysioPy. All right, so once we ascertain that the data is looking good, and that's very important, by the way. Always look at your data. Always check that the data is good. In my case, I'm lucky. This subject was performing very well, and it's very good data, so I don't have to correct too much. But it might happen that that's not always the case. So we're going to now start the initialization of the automatic peak detection, and I'm going to do this with setting a threshold and a distance. So basically, threshold and distance is something that is used by the automatic peak detection algorithm to decide where to put peaks. It's not just the maxima of the function. The threshold tells us basically if we want to have the peaks above a certain amount in basically the distribution of the array itself. In this case, I'm choosing 0.1, which corresponds more or less to the 10% of the distribution, because I've seen I've looked at the data. I've seen the respiratory changes, the respiratory fluctuations, and not all of the peaks are tall, but they are all true in my case, and so I'm choosing a very low threshold because I just want most of them to be found automatically. The distance of 60, it's basically 1.5 seconds every 40 hertz. Sorry, 1.5 seconds at 40 hertz. And it's a good distance for respiratory data. You can increase it a bit more if you know that your subjects are breathing a bit slower, as they should. It's fine. But in my case, I prefer to have this distance. Once that's done, I am going to run the operation itself, that is the filter physio operation, which is going to use my, sorry, it's not the filter physio operation, my bad, it's a peak find physio operation, in which case I'm going to use my object. I'm going to set the threshold to the THR of 0.1 as I said before, and the distance to my distance 60 points. I'm going to run it super quick, and now it's where actually peak that shines, one of the 2 points at the very least, which is basically the possibility to edit the physiological data peak detection. So I'm going to run this command. If you have issues running these commands in this educational course. And finally, you will need some physiological data. Today we're going to work with cardiac and respiratory values. If you have some at hand, that's great. Otherwise, you can check out again this repository, github.com/asmoia/OHBM 2023 noise tutorial for some test data to play with. All right. So the first part, I'm going to switch between the